Hello everybody, we're CSE 15 and today we're going to be presenting on enhancing indoor localization using ML models with the IEEE 802.11, so that's Wi-Fi protocol. My name is Rafael Castro.
My name is Ella.
My name is Axel.
And I'm Pranay, Kocheta.
So to start it off, we're going to be answering the question, what is localization? So localization is when a machine or system is able to pinpoint a user's location to a very high accuracy. So outdoors, we have a really good system for this that you've probably all heard of, called the Global Positioning System, or GPS. And this works through a network of satellites that basically kind of send a signal into you, and they're able to triangulate your location. However, indoors, this doesn't really work as well due to things like, for example, roofs that are blocking the signal. So we have to develop other types of indoor localization systems to kind of combat this problem. Researchers are using radio frequency or RF systems in order as to kind of find out where you are. And three examples of RF frequencies that we're using are ultrasound, infrared, and Wi-Fi, which each have their own cost and benefit. But we're going to be focusing on Wi-Fi, and one thing to notice is that Wi-Fi is an awesome RF signal to use just because of how deployable it is due to the fact that a lot of indoor spaces already are equipped with Wi-Fi.
So let's talk a little bit about what Wi-Fi localization actually is. It's basically using the Wi-Fi beams that already exist in an area along with the Wi-Fi beams that are coming out of your own personal devices to help figure out where you are relative to your space. This can be done through multiple different types of pieces of data and also multiple processing methods such as machine learning. I'll get into the data in a moment, but this can be implemented into many different spaces. For example, shopping malls, homes, office buildings, and more. Any place that GPS doesn't work. So let's talk a little bit about the type of data that Wi-Fi contains that you can actually use to localize areas, right? There's four key kinds, which are channel state information, which this project is going to focus on, but there's also received signal strength indicator, time of flight, and angle of arrival, which we'll also continue to explain after this. Also, in terms of some of the technical details for this project, in this project we used the ESP32 chip, which uses Wi-Fi 4. Although the most recent version, or the most commonly used version of Wi-Fi is Wi-Fi 5, we chose to use the ESPs on Wi-Fi 4 because it's the first generation to introduce CSI type data, channel state information, and so we wanted to prove that if we can get it working on the very first generation of CSI, then there's so much future potential as Wi-Fi gets better and better.
So a wireless signal like Wi-Fi can travel in two different ways. It can travel in a line of sight path, which is basically when it travels directly from the transmitter to the receiver with no interference from the environment. And secondly, it can travel in a non-line of sight path where there's scattering, reflection, and absorbance from the environment. For example, it can get scattered by walls and ceilings, and this multipath signal may contain useful information about its environment.
So kind of building off of that, as Ella said, due to the fact that the signal is really going to go everywhere due to the multipath, we can get really fine-grained information about this environment from the wireless signal received. So researchers have developed a function known as channel impulse response, or CIR, that accurately reflects the impact of multipath modeled by little h of t. And you can see that, obviously in that diagram, there are going to be several different paths where the signal can be reflected or partially absorbed by a wall. And different things like the complex attenuation, phase, and time delay of each component are all going to be modeled in that CIR function. So then we can see CIR is in the time domain, but if we use a Fourier transform, we can actually convert this to channel frequency response, CFR, by switching it to the frequency domain. This leads us to CSI, which is represented as a matrix H, and this just basically contains the CFR of multiple antennas in a receiver. And just because this contains so much information from so many different angles, CSI is a really good tool for wireless sensing, as it contains a really good fingerprint of this environment. So since CSI is a matrix, and you're going to have one matrix for each different point in time, this is kind of how you would plot, for example, two pieces of information you can get from CSI, the amplitude and the phase. So you can see there are several different subcarriers that you can plot here, and this is all one big continuous signal over time.
So commonly used algorithm in Wi-Fi localization is the music algorithm or the multiple signal classification algorithm. It's a subspace-based direction finding algorithm that basically estimates the angle of arrival, which is the angle at which a signal arrives at the transmitter, the receiver from the transmitter. So there's an array of antennas that collects signals, and then the music algorithm uses linear algebra and eigenvalue decomposition to calculate the music spectrum and get the angles of arrival.
Another metric we can use for localization is received signal strength indicator, or RSSI. This is a value that says essentially how strong a connection is. If there's less obstruction or closer distance between access points, you'll have a higher value. While this is useful more for coarse-grained data, it lacks in the area that it does not provide a lot of information about the environment as a whole, and it therefore is not always good for indoor localization. And then another method we can use is time of flight. This uses the basic formula distance equals speed times time. We can find the time by knowing the difference between the time of transmitting a packet and receiving it. And notably, this method does not require the clocks of two devices to be synced, because that is a very advanced process. And while this method works very well, it is limited in the frequency of the device, as it heavily determines the accuracy, and it also performs far worse at close distances.
All right, finally, let's talk about angle of arrival. As Ella was explaining earlier with the music algorithm, this is basically what it's trying to arrive at. And so angle of arrival is basically just using the phase difference between the antennas in CSI to then apply some math and figure out where is the data being sent from. But the thing with angle of arrival is it's not normally used as an independent form of localization, but rather used to enhance other methods of localization, such as CSI, RSSI, and time of flight. And you can see us trying to calculate angle of arrival on our own.
And here's a color-coded table we made of the four methods we described to try to give you a visual overview of the benefits and the drawbacks.
Let's move on.
So we collected our own CSI data using 2 ESP32 chips and 2 devices. So even though there are publicly available CSI datasets online, they're limited in distance and are often too clean, which is why we collected our own CSI data, and we collected data at distances of 1 to 20 meters indoors, and we measured the distances using a laser.
So with this data we collected, we decided to train our own models. So the first was an extreme gradient boosting model. This is a sequential model built off of decision trees. It is very efficient and very powerful for that reason. And with our data, we were able to achieve a 95.2% accuracy.
Another model we thought would work really well is lasso regression, which is a regularization technique that applies a penalty to certain features in a data set that it's analyzing to prevent overfitting. So we thought this would be really good for CSI data due to the really high amount of self-carriers. However, even when trained with an alpha value of 0.1, the accuracy was only about 74%. So now we're going to be talking a little bit of our own individual projects. So as we mentioned, CSI is something that's really sensitive and that can be used for a variety of different things. So in addition to the work we did for localization, we wanted to see what else we could do to expand on this field. So I'll go first with my project Identify, which uses Wi-Fi channel state information, or CSI, for fine-grained 3D gesture and pose recognition. So, as software, kind of gets more sophisticated, we need, more accessible and intuitive ways for humans to interact with computers. So, if there's a software that, for example, would require the use of your hands in a three-dimensional space, it's imperative to have, not just something that's accurate, but something that's really accessible to everyone, So that's also, a great reason why we would want to do this with Wi-Fi CSI data, as again, Wi-Fi is very, very common in indoor spaces. First off, we were able to do some literature review and see that coarse-grained gesture and pose recognition has been done. So, differentiating between different gestures and poses, like, something like this, and that's coarse-grained, so that's not really very detailed. There's been work done in fine grain as well. So even tracing numbers in the air, has been picked up by CSI data. And coarse grain gesture and pose recognition has been done in 3 dimensions. As you can see by this 3D gate skeleton, that was just modeled based off the CSI data. However, you can see, for example, in the skeleton, for the hand, it's just a dot, right? And it doesn't really show the specific gestures. That could be this, that could be that could be anything. So next slide, please. What I wanted to do is, kind of collect more data on this and see if we can get this a lot more fine grained. I'm using the Open Pose library to track the hand position here, which provides 3D data. And at the same time we're going to be collecting this, we're going to be collecting CSI data in an empty room as well. And finally, we're going to use data processing in really well-known ML models to analyze the CSI data and be able to predict that 3D position for the user's hands.
My project is called SleepFi, where I will use Wi-Fi channel state information in combination with LLMs to track and advise individuals on how to improve their sleep. So sleep is obviously very important, as it's a very significant factor in our physical and mental health. And while there is existing research in using radio frequency to track sleep health, these generally focus on disorders like sleep apnea and are common, expensive, and usually require a technician or a doctor to interpret the data. So I propose a solution that uses the common Wi-Fi access points in households around the world, uses channel state information in combination with LLMs to not only track these key metrics determining sleep health, but using large language models to combine this data with context and advise the person on how to improve their sleep quality. This is a proposed setup with Wi-Fi access points and a person sleeping in between them. So once I collect the CSI data, I will use various filtering, smoothing, and machine learning algorithms to track the heart rate, sleeping positions, and movement, as these are factors that I found to be highly correlated with sleep cycles, sleep stages, and also overall sleep health. So with this data, in combination with the context I just mentioned, I will fine-tune a ChatGPT model that will give advice to the person on how to improve their sleep, considering the previous night, as well as their historical sleep data, and give them key ideas to improve their sleep health.
So my project was YFence, where I used CSI data and deep learning for geofencing and human presence detection. So in the past, people have implemented human activity recognition systems, but I focused specifically on geofencing, where I detect if there's a human present in a specifically defined area, and that can be scaled using different numbers of ESP32 chips. So I collected data using 2 ESP32 chips, and I collected data of an empty room with 1 human and with 2 humans, and then I created spectrograms for each of these categories as input to my CNN model. The spectrogram, one of the spectrograms can be shown here. It shows like the amplitude of different frequencies, and I use the CNN model to predict if there's human presence in the area, and this can be applied in security and also smart homes.
All right, finally, my project is PulseFi, which is basically a low-cost, robust machine learning system for accurate cardiopulmonary monitoring using CSI. Basically, what this is vital monitoring such as heart rate and breathing rate, specifically for people who are like older or in like senior care, right, in their own home environment where they need the vital monitoring more than your average population, but they don't often have access to it in a non-invasive way. Then the current limitations with these setups is they often use these very expensive setups like with triple antennas and full like devices powering them, or they've just only been trained on like a very low range or single individuals, and so they can't handle the diverse population. And finally, non-invasive methods such as cameras, or there's camera-based methods which are highly invasive. And so PulseFi aims to solve all these problems by using the ESPs, which is a single antenna low power system, which is cheap and it'll work on higher ranges and be trained on a variety of people, while also taking real-world action by creating a database for each individual person, calculating their averages, and then notifying them when anything is off based on that. And so let's talk about the current results I've achieved. We collected data on 1, 2, and 3 meters with 8 people, collecting over 380,000 samples, and we used a ground truth finger-based sensor and frame extraction to get that, and the ranges exceed far past like the US normal ranges, so it's able to handle full ranges. But in terms of model performance, using an ensemble model of 5 different models on breathing rate, we achieved an overall performance of 1.5 breaths per minute error, and in terms of heart rate, using a custom LSTM architecture, we achieved a performance of 1.17 beats per minute error, which also happens to be the state of the art at 3 meters, as far as I could find. This is like the data collection setup and also some of the model performance. The bottom is the heart, the top is the breathing rate.
All right, thank you so much to our mentor, Nana Matia, who's done an excellent job guiding us, so thank you very much to him.